All right, so we just took a look at 5.1, which is taking a look at static and dynamic equilibrium and solving those problems. And in all of those cases, there is no net force, and therefore the acceleration is equal to 0. Now, we did look at some of the forces as mass times acceleration, but now we're going to look at Newton's second law. And in this case, in Newton's second law, when dealing with dynamics, we will have an acceleration. So an acceleration will not equal 0, and we'll have to solve problems based on that. Again, we'll look at free body diagrams, we'll look at the forces acting, and those will get us the acceleration through the net force. So with Newton's second law, Newtonian mechanics comes down to two main steps. First off, the forces acting on an object will determine its acceleration. Okay, the forces determine the acceleration, and we use the formula acceleration is the net force divided by the mass, and we can get that acceleration using the concept of forces, or we can use it with kinematics, and those two things help each other out. So with dynamics and Newton's second law, the sum of the forces equals mass times acceleration. And again, those are independent in each direction, or each dimension, the x direction, the y direction. Now, with Newton's first law, we just set these equal to 0. Now we're saying acceleration is not 0, so they are not equal to 0. Okay, so let's go ahead and start with an example problem. And it says a golfer putts a 46-gram ball with a speed of 3 meters per second. Friction exerts a 0.020 Newton force opposing the ball, causing it to slow down. Assuming the direction is okay, will her putt reach the hole 10 meters away? All right, so again, we have a lot going on. And the question is asking me, I putt the ball, it's going some velocity, will it go some distance? So if I were to draw just a quick picture of this, the ball needs to make it into the hole, and that is 10 meters away. The ball is traveling at 3 meters per second, but it's undergoing some friction that's going to slow it down. So let me draw a free body diagram of this. And we know that there is a weight force on the ball. We know that there is a normal force on the ball. Those two are balanced, right? It's not accelerating up or down. So those are in equilibrium. However, because of friction is unopposed once she hits the ball. So this is our free body diagram, and we do in fact have a net force that is equal, or caused by, I should say, the force of kinetic friction. So there's two kind of parts to this. The part one is on the left. And with that, I want to use kinematics to figure out if she makes it into the hole. Part two on the right, I need to use dynamics to understand the net force, which gets us our acceleration, to plug in to our kinematics. Okay, so this picture is getting a little messy. So I'm going to go ahead and redraw it, and we'll pick up the video from there. Okay, so here is a better simplified version. I do have my my free body diagram all the way over on the right, and that free body diagram shows me again the net force. Now this can get a little confusing because the pictures have arrows going in different directions, but the ball leaves the putter and heads to the right. Acceleration is to the left because it is a negative acceleration. It is slowing the object down, and we see that in both pictures. So right here on the far left, this is my kinematics, and on the far right, this is my dynamics. And I need both to solve this particular problem. Okay, so I need to look at my formulas, and I know that the sum of the forces, and I did it quickly here, but the sum of the forces in the x direction equals all the forces acting in the x direction. Well, there is no normal force in the x direction. If I were to, again, I'm listing all of the forces, just like I did in the last unit. There is no normal force, there is no weight, and therefore the only force I have acting in the x direction is the force of friction. Now I also have the y direction, but with the y direction, this is an equilibrium. So I actually don't care about this at all because there is no motion happening really in the y direction. So I'm just going to get rid of that. And I'm left with that the negative force of kinetic friction, or rolling friction, whatever you want to talk about, is equal to the mass times the acceleration. So if I solve for the acceleration, I can do that by plugging in the frictional force of negative 0.020 newtons and divided by the mass of 0.046 kilograms. And I get a acceleration then of negative 0.435 meters per second squared. From getting that acceleration now, I have this is part of my toolkit, and I need to figure out how far the ball actually goes. Now there are a few different ways that I can go about solving this. You can see one of the ways right here. This is using the concept of VF squared equals VI squared over 2A delta X, and then solving for XF. The other thing I could do is I could say XF equals XI plus VI delta T plus 1/2 A delta T squared. And the problem with that is I don't know the time. So I could solve for the time that it would take to slow down to rest using VF equals VI plus A delta T. But now I'm getting all this extra work in, so I'm actually not going to use this. So this formula that is used right here, understand that it just came from VF squared equals VI squared plus 2A delta X. And all I did was I split up delta X into XF minus XI, and then I moved the XF over to the other side. So if I go ahead and plug in, the final velocity is 0 meters per second. The initial velocity is 3 meters per second, and that quantity is squared, divided by 2A, which is 2 times negative 0.435 meters per second squared. I get my final answer of a distance of 10.3 meters. So I know that the ball goes 10.3 meters. The hole is only 10 meters away. Therefore, I know that it's going to make it into the hole. And I can figure that out just by looking at the magnitude of the friction force and how much the object weighs. So we have a partner problem, which we'll take a look at tomorrow as with your partners. And it says a car with a mass of 1,500 kilograms is being towed by a rope held at a 20-degree angle. This problem sounds really, really familiar because we did it almost identical. But now we have a frictional force of 320 newtons opposes the car's motion. What is the tension in the rope if the car goes from rest to 12 meters per second in 10 seconds? Now, this is actually somewhat tricky because as we accelerate, the tension in the car is no longer equal and opposite to the force of kinetic friction. Or I should say the x component of tension, as we saw in the last problem. As we accelerate, we increase the tension in the cable. So the tension will actually be greater than it was in our previous example problem because of that acceleration. It causes the tension to be greater. So we'll take a look at that problem tomorrow in class. We will also have another partner problem tomorrow, and this deals with a sled of a mass of 20 kilograms, slides along a frictionless ice at 4.5 meters per second, and then it crosses through a rough patch of snow that exerts a frictional force of 12 newtons. So imagine you're going across ice because you were sledding across ice, and then you go off the ice into the snow. That snow is going to cause you to slow down. So we want to know how far does it slide before coming to a rest. So for these two problems, just take a couple minutes and set up a free body diagram, and that'll help us as we go into the problem tomorrow in class. You can also, if you want, even set up a pictorial representation that'll help us visualize the problem a lot better. And that is our introduction into solving Newton's laws. Now, for these problems, you saw that we got simple, really easy numbers like a frictional force of 12 newtons. So for the rest of chapter 5, we're going to dive a little bit more into each type of force, kind of figure out how we quantify each type of force, and then we'll continue to solve problems based on that. So right now, you're getting things like 12 newtons, okay? Super easy. But where does this come from? And this is this kinetic friction, for example. Then the force of kinetic friction is equal to the coefficient of kinetic friction times the normal force. So we're going to get into understanding where these numbers come from and dive deeper into the quantitative examples that we can do. And we'll do that right away in the next segment.